So there are properties of waves that we're going to be discussing because it's kind of a setup for understanding sort of the properties of electrons and matter in general. Uh, these are interference and diffraction, and the simple idea is if two waves interact constructively, they reinforce or amplify each other. Um, and then if they interact destructively, they cancel each other out. Okay, they essentially are subtracting. And the other property of light we'll be looking at is diffraction. And when light goes past a corner, it has this uh, essentially ability to bend around a corner. And we'll talk about these things in the next few slides. A little bit more about interference. Interference is when two waves interact. Constructive interference is also known as in-phase interaction, and destructive interference is what we call out of phase. And so this is what we mean by phase. If you remember what a sine wave looks like, so a sine wave looks like this, right? And it's often described as the function is sine omega t, and then there's this term that goes along with it. T would be time. This is our x-axis. All right. Omega is just sort of related to how quickly the sine wave goes up and down. It can be constituted as something like the frequency. And then phi is the phase. So when we say something is in phase, that means and this value of phi, what it does to the wave, let's say you increase it. Let's say this is your sine wave when phi is 0, and you increase it, then what happens is it shifts over. Okay, so when we say two sine waves are in phase, what happens is their functions are such that the phase makes them line up like this one. Okay, so here's 0, and here's another 0 line. These are oscillating up and down together, so this would be in phase, right, interactions, and this would be leading to what we call constructive interference. And in essence, what you're doing is you're just adding these waves together, and you end up getting a larger wave. Now, when we think about out of phase, right, that means the phi, the value of phi, is such that we would say they're 180 degrees out of phase with each other. You don't need to know that particular term, but it's because when something's 180 degrees in terms of a sine wave, as one is going up, right, the other one would be going down. And so if you take these two and add them together, remember, I'm just going to make some highlights here. When I do this, what I like to do is use blue to represent the positive like this, right? And then red to indicate negative. That's sort of a standard or traditional color coding. So this would be negative down here like this. So what happens in essence? Oops, I did that one wrong, huh? This one would be the negative like this, and this one would be the negative like that. And now I got to get my blue one out. Before I do that, I wanted to point out that these would be the negatives down here, okay? And the positives would be all these upper sections where the amplitude is positive, okay? So, and again, this is like a 0 line here. That represents 0. So if I take these two positive sections and add them together, they just get bigger. And these two negative sections also get bigger, but in the downward direction. So your amplitude is increased. And that's in phase interaction. And when it's out of phase, what ends up happening is every part that's positive cancels every part that's negative. Remember, these are just numbers, right? So they end up canceling each other out, and we get decreases in amplitude. And so this is the behavior of things that traditionally we describe as waves, like water waves, sound waves, and now light waves. We describe light waves in the same way. So light has these properties, which is why it's considered to be a wave. One of the reasons why it's considered to be a wave. One of the other things that we consider is diffraction. So when waves encounter an edge or an opening, they bend around it, and that process is called diffraction. And if you were to think about like a tube like this with an angle on it like this, right? And you put light like this, right? If it's a particle, it travels straight. So like if you were to throw sand down the pipe, it would be traveling in a straight line. On the other hand, if it's light, it has the ability to be there for the light to bend around that edge. And that is definitely a property, again, of waves. So what we're going to look at next is what happens when you put openings in a sort of a barrier, okay, and then we pass light through them. So we're going to pass light waves, and waves are often depicted as wave fronts. So we're looking at waves that look like this, and we're going to put a line like this at the top of every wave, okay? So let's do this in a slightly different color. We'll do it in green. So that's what we're going to do here, okay? So we have waves going like this. We have waves going like this. And that's representing just the crests or the tops of the waves. When it hits this opening, what ends up happening is the light bends and the crests look like this now. They have the same frequency being determined by their spacings and their speed, right? Or the same wavelength. So these will have the same wavelength, but they spread out in that fashion. The same thing will happen over here. Again, this is a wave property. If you threw BBs at this opening here, the BBs would just all go straight through. There's no diffracting around the edge and spreading out for particles, okay? So this is probably a better view, but it's the book's picture, right? This is wave diffraction. Wave diffraction, these are the wave crests. And as they hit the slit, they begin to spread out. And then for particles, the behavior you expect to see in diffraction is when you shoot them at a slit like this, what ends up happening is you'll get a whole bunch of them right here, but none would be here and none would be here. And the rest of them that hit this sides here would just be stopped at the opening, at the sides of the opening. So this is what happens when you do light waves or water waves, either one. You have, again, this light, you have a light source and it's creating waves. Again, these represent the peaks or the troughs, and these are the wavelength. As they hit the opening, their wavelength should stay the same. And then what happens is these waves make these circular patterns, and eventually they hit along the wall over here. Now, what you see on this wall is going to be the combination of constructive and destructive interference as these waves begin to interact with each other. So if, for example, you're looking at these dark regions here, like this one here, what's happening is the light waves are out of phase from each other, because you think about how the waves are moving. At this point here, this path is a different length than this path, and what ends up happening, even though the waves have the same frequency, are traveling to the same point, they have different distances they travel, and what ends up happening is they get out of phase with each other. Okay. Now, if it just so happens that the two waves, right, actually come to a point and are in phase, then what happens is you get bright spots. Okay, so this is in phase bright spots where the paths, they may not be the same, but they have they're not the same length, but they are some multiple of the wavelength. So the difference between these is always some multiple of the wavelength, and what ends up happening is the waves are both large when they strike the wall at this point. Here it's such that they're off by a half a wavelength, and so that means like a half a wavelength is from, let's say, here to here. They're off by that much. And that's what causes the constructive or destructive interference. Okay. So this is definitely what we expect to see when we see waves. Okay, so we get two things. We get diffraction, right? And we get interference. We get both constructive and destructive interference. This pattern that we would see is known as a diffraction pattern.